Hi guys, welcome to the video on how to solve gas law problems without memorizing any of the simple gas law equations. In this video I'm going to show you how to use PVnT tables. The PVnT tables are, like I said before, a way to solve gas law problems without having to memorize any equations. All you really need to understand are the relationships that exist between two variables. So can you name the relationship between pressure and volume, or pressure and temperature, or volume and temperature? So this goes along with the activity that you did in class, along with video 3.2. So for each gas law problem, again, this is just going to be for the gas law problems like Boyle's law, Charles' law, not the ideal gas law. So this is for the simple gas laws. What you're going to do is you're going to make what's called a PVnT table. I'll show you how to make one of these, but then you're going to fill in the given initial conditions and final conditions for P, V, N, or T. If there are any variables that are held constant, you will cross those out. And then you will decide how the change will affect the starting quantities. This is where the relationships between the variables come into play. And then what you're going to do is you're going to multiply your given information by the appropriate factor to get the final value. And so basically what you're doing is you're taking your given and you're multiplying it by a fraction. So what we're going to do is we're just going to go through an example. We'll go through a few examples just so you can see how the PVnT tables work. If it's something that you're interested in, you can use it. If not, you can just go back and memorize the gas laws. So for this first example, it says the gas pressure in an aerosol can is 1.5 atm at 25 degrees Celsius. What is the pressure when the can is heated to 450 degrees Celsius? So what I'm going to do first is I'm going to label my variables. So here is my initial pressure. Here is my initial temperature. It also gives me my final temperature, and I am trying to find final pressure. So notice, if you wanted to go back and use the gas laws, you could, right? You could use Gay-Lussac's law if you wanted, but we're going to look at how to do it without having to memorize any equations. So the first thing we're going to do is we're going to make a PVnT table. And what that looks like is we have P, V, N, and T. And then we have initial, final, and effect. So here is our PVnT table. Okay, what this is your initial condition, final condition, and what the effect was. So with our pressure, okay, they give us P1 right here. So I'm going to fill that in, 1.5 atm. They also give me temperature. Now, in order to use any gas law problem, what unit does temperature need to be in? It needs to be in Kelvin, so we need to convert this Celsius to Kelvin. You add 273, and so your temperature is 298 Kelvin. Now, they want to know what my final pressure is, so I'm going to put a question mark in here by final. And they tell us that our final temperature is 450 degrees Celsius. Again, you cannot use Celsius, so add 273, right? K equals C plus 273. And so we get 723 Kelvin. Now, did the problem say anything about volume? No, so I'm going to cross it out. Did it say anything about number of particles or moles? No, I'm going to cross that out as well. So I now have P and T, and I'm comparing them. So in this effect row, this is where we're going to look at the conditions that changed, right? So the conditions that we changed. So what was the effect on temperature? What happened to temperature? It went up. Okay? If temperature goes up, what does that mean happens to pressure? Well, if temperature goes up, That means that our gas molecules are moving faster, they're colliding more with each other and with the wall, and collisions are the same as pressure, or pressure is measured based on collisions. So the higher the temperature, the more collisions, the higher the pressure. So our pressure is increasing due to temperature. So now, we have filled this PVnT table in. We've looked at how it changes. Now what we have to do is we have to multiply by the appropriate factor. So start with your given piece of information. Our given piece of information is actually the pressure, right? Because we have to start with our initial pressure in order to determine the final. So I will start with 1.5 atmospheres. Now I have to multiply by a fraction. Okay, and my fraction that I multiply has to be based on this effect. So if you want a number that is larger, you're going to multiply by a large fraction, right? A high numerator. If you want your number to get smaller, you're going to multiply by a small fraction, which means you're going to multiply with the smaller number on top. So if we look at this, okay, our pressure needs to increase. If our pressure needs to increase, we're multiplying by a factor with temperature. So if we want pressure to increase, do we need to multiply by a large number or by a small number? Multiply by a large number. So I'm going to put 723 Kelvin on top, 298 Kelvin on the bottom. Now notice our Kelvin units actually cancel, which is good because I started with pressure as my unit. I want to end with that as my unit. So to solve this now, we multiply across the top, we divide by what's on the bottom. So we do 1.5 times 723 divided by 298. When we round to, let's see, two significant figures, we will get 2.1 atmospheres. Now check your answer, right? So our answer is greater than our initial. Does that make sense? Yeah, that makes sense because our pressure should have increased because temperature increased, and it did. So that is an example using a PVnT table. Really, you're just taking your given and you're multiplying by a fraction to solve for your unknown. So now what I want you to do is I want you to see if you can solve this second example using the information that we went through in example 1. So can you set up the PVnT table, can you fill it in, and then can you multiply by the appropriate factor? So to start out, I'll start it out with you. The first thing that you want to do is read through the problem and label your variables. So what would be the new pressure? So what would be the new pressure? So I'm going to be finding P2 if 250 centimeters cubed. Well, what is centimeters cubed? It's the same as milliliters. So this is V1 of gas at standard pressure. What is standard pressure? Okay, typically we use ATM, so 1 ATM. So that's P1, right? So we have 250 milliliters of a gas that's at 1 ATM, and we compress it to a volume of 150 milliliters. So that's V2. This corresponds to the new pressure that we're trying to find. So now, set up your PVnT table. PVnT. Okay, once you've set that up with initial, final, and effect, our P1 is 1 ATM. Okay, our V1 is 250 milliliters. Our P2 is what we're trying to find, and our V2 is 150 milliliters. Now you might be thinking, well, what about units here, right? What about the units that are in our PVnT table? You just need to make sure units are the same. Right, so if you have milliliters for volume 1, you need milliliters for volume 2. If you have ATM for pressure 1, you need ATM for pressure 2. The only thing that absolutely has to be a specific unit is temperature. It has to be in Kelvin. Pressure could be in torr, it could be in bars, volume could be in milliliters or centimeters cubed or liters or deciliters, right? As long as they're the same. The only thing that needs to stay constant in terms of unit is temperature. It has to be in Kelvin. So we now have our PVnT table filled in with the information from the problem. It said nothing about N, it said nothing about T. So we assume that it stayed constant. So now we're comparing P and V. So when when volume goes down, right, our volume is going down, what has to happen to pressure? Well, if volume is going down, that means you are compressing the gas. You will then have more collisions. Your particles are going to collide more, which means that your pressure is going to go up. So it's going to go up due to volume. Now, again, take the initial of what you're trying to find, 1 atm, and you're multiplying it by a fraction. Okay, so if we look at this effect right here, pressure has to go up due to volume. So that means with these two volume numbers, I need to multiply by a number that is large. So I'm going to multiply by 250 milliliters over 150 milliliters. Again, your milliliters cancel, one on top, one on bottom. We're left with atm, which is what we want. So 250 divided by 150, you can even do this without a calculator. The zeros cancel. 5 goes into 25 5 times, so you have 5/3. So that is 1.67. We have to actually round to two significant figures, 1.7 atm. Now, the question is, does that answer make sense? Right? Does it make sense that you started out with 1 atm and you're ending with 1.7? Well, yes, because we even said right here that pressure needs to go up. So now this third example, if we read through it, it says that an inflated balloon has a volume of 6 liters, so here's V1, at sea level, which is 1 atm. And it's allowed to ascend until the pressure is 0.45 atm, so there's a new pressure. I'm going to write P2. During ascent, the temperature of the gas falls from 22, so it's from 22, which is my initial, to negative 21, which is my final, T2. It wants us to calculate the volume of the balloon at its final altitude. So in this case now, we have 3 variables. So if we set up our PVnT table, and we fill it in, initial, final, and effect. Notice that we did not label N anywhere, so I'm going to cross that out. Now, I'm going to fill this in based on the numbers that I've labeled. So V1, my initial volume is 6 liters, my initial pressure is 1 atm, and my initial temperature is 22 degrees Celsius. But remember, in order to put it in, we need Kelvin. So remember, K equals C plus 273, and our initial temperature is 295 Kelvin. Okay, now let's fill in our final. So our pressure becomes 0.45 atm, volume is what we're trying to find, and temperature actually becomes 252 Kelvin. So now what we're going to do is we're actually going to determine what happens to volume based on both of these changes. So temperature, well, let's start with pressure. Pressure went down, so if pressure goes down, what happens to volume? Well, these are inverse, so volume will go up due to pressure. Then temperature is going down. Okay, if temperature is going down, what happens to volume? Volume will go down, right? Those are direct. So now notice we have 2 relationships in this effect row. Now, as before, you start with the given that is related to the unknown you're trying to find. So I'm going to start with 6 liters. Now instead of multiplying by one fraction, I'm going to actually multiply by 2. One is going to be based on pressure, one is going to be based on temperature. So what I'm going to do is, let's start with pressure. Volume has to go up due to pressure. So volume has to go up due to pressure. That means I need to multiply by a large fraction. So that means I'm going to put my larger number on top. So 1 atm over 0.45 atm. And then my volume needs to go down due to temperature. So that means that when it comes to the temperature fraction, I need to put the smaller number on top. So now what we've done is we've taken into account both pressure and temperature, and now we multiply this just like any dimensional analysis problem. So we take 6 times 1 atm times 252, and then we divide by what's on the bottom. And what you find is that your answer, we get 11.39 liters. And notice we still only have 2 significant figures, so 11 liters. Now, you might be asked a question that says, which had more of an effect, the pressure or the temperature? Well, if you notice, my initial volume was 6 liters, my final volume is 11 liters. So my volume actually increased. So if my volume increased, which of these two variables had more of an effect? Well, the pressure probably had more of an effect, right? Because if temperature had more of an effect, volume would have decreased. But it didn't. It increased. So pressure had more of an effect. So these are just some examples using these PVnT tables. It's just another way to do these gas law problems, and once you get the hang of it, it's actually pretty simple, and it keeps the relationships in your mind. So like if pressure goes up, volume goes down. If pressure goes up, temperature goes up. If number of moles goes up, pressure goes up. So it's important that you know all of those relationships as well, but now these PVnT tables also bring the math into it.